So let's consider a boat moving on the water. Let's assume the boat's motor is pushing it forward at 6 meters per second. So the boat is going to travel 6 meters further every second in whatever direction it happens to be pointed. So we could think of that as the speed the boat would be moving on still water, forwards at 6 meters every second. But what if the water wasn't still? What if the boat's on a river? So we're on a river where the current is flowing to the right at the rate of 5 meters a second. So if our boat's engine was off, it would still be moving. It would be traveling downstream at the rate of 5 meters every second. So here's our question. What if we point our boat directly across the river and set the engine to push it forward at 6 meters a second, while at the same time the river is carrying the boat downstream at 5 meters a second? Hopefully it's fairly obvious that the boat will neither go directly across the river nor directly downstream. So here's our first question. In what speed and direction will the boat actually travel? Well, our basic principle is when two or more vectors act on a point at the same time, their combined effect is found by adding the vectors. So we can think of our boat as having two velocities. It's moving in whatever direction it's pointed. Let's call that the motor velocity. So I'm going to use Vm to mean the motor velocity. And that's 6 meters a second. In whatever direction the boat's pointed, we were pointing our boat straight across the river, and in that context that was towards the top of the screen, so let's call that north. At the same time, the river current is carrying our boat downstream to the right at 5 meters a second, so I'm going to call that the current velocity, Vc, and that's 5 meters a second. In the context we were looking at, that's to the right. Let's call that east. The combined effect is going to be found by adding them. So what the boat will actually do, what I'm going to call its net velocity, is the sum of the motor velocity and the velocity due to the current. The motor velocity is 6 meters a second north, and the current velocity is 5 meters a second east. We can't just add the numbers, we have to take directions into account. So we need to draw our vector addition diagram. So we'll start off by drawing our vector pointing north, 6 units long. That represents the speed the motor and direction the motor is pushing the boat. Now we're going to add the current velocity, 5 units pointing east. And so our net velocity is the one that points from where I started to where I ended up. So the length of that vector will be the speed the boat will actually travel, and the direction that vector is pointing is the direction the boat will actually travel. So we're going to have to figure out that angle there. So we've got a right angle triangle. The length of that net velocity vector is just the hypotenuse of the triangle. So the length is going to be the square root of the motor velocity squared plus the current speed squared, which is the square root of 6 meters per second squared plus the current 5 meters per second squared. And when I do the math, I end up with an answer of approximately 7.8 meters per second. So the boat will travel at an actual speed of about 7.8 meters per second. To get the direction, I need to use some trigonometry. The current speed is the side opposite the angle. The motor speed is the side adjacent. Opposite over adjacent is tangent. So that angle is going to be the inverse tangent. And I'm running out of space here, so I'm going to just shorten my explanation. The inverse tangent of the current over the motor, so the inverse tangent of 5 meters per second over 6 meters per second, and to the nearest degree, that is 40 degrees. Now that's the angle in the triangle. What's the direction? Well, our boat was pointed north. We're going 40 degrees to the east of that. So what our boat is actually going to do, it's going to travel at 7.8 meters per second in a direction of 40 degrees east of north. Okay, when we go back to our boat, whoops, wrong one, boat there, let's give it an initial speed of 6 meters per second. Let's set the current flowing east at 5 meters per second, and when we start our boat, we can see that that's basically what it does. We can show our net resultant there. That red vector represents the speed and direction the boat is actually moving. Okay, question number 2. How long will the boat take to cross the river? So, the basic relationship you should already know is that the speed something travels at is just the distance it travels divided by the time. Let's assume for our purposes here that the river is 100 meters wide. To find the time, just doing a little bit of algebra there, the time will be the distance traveled divided by the speed. So we're crossing a 100 meter wide river. The trick on this question is to use the right speed. So remember, our boat is pointed that way. It's traveling 6.7 meters every second. That's what we just, no, sorry, 7.8 meters every second. But it's not crossing the river at the rate of 7.8 meters every second. It's 7.8 meters away from where it was just 1 second ago, but that's on an angle. It is still only 5 meters further across the river. No, 6 meters further across the river, and 5 meters further downstream. So the actual speed of the boat is 7.8 meters a second, but that's made up of those two separate motions. It's 6 meters further across the river every second, and it's 5 meters further downstream every second. We want to know how long it takes to cross the river, so we need to know how fast is it going across the river. And it's still crossing the river at the rate of 6 meters per second. And to the nearest second, that gives us a time of 17 seconds to cross the river. So the trick in answering a question like that is to pick the correct velocity. Next question. How long will the boat take? How far downstream will the boat be when it reaches the other side of the river? So once again, our boat is traveling, that's our boat is traveling on some angle at 7.8 meters every second. But that's on an angle. It's still only going 5 meters further downstream every second and 6 meters further across the stream. So if I want to know how far it will travel downstream before it reaches the other side, well, the distance it travels is just the speed multiplied by the time. But again, the trick is using the correct speed. It is traveling downstream at the rate of 5 meters every second. And we just previously calculated that it's doing that for approximately 17 seconds. So it's going to end up about 85 meters further downstream. So that's our river. We point our boat directly across the river. The river's carrying it downstream, but our boat's actually going to travel on a line something like that. And it's going to take 12 seconds to cross the river. No, it's not. It's going to take 17 seconds to cross the river. And when it crosses the river, it will be approximately 85 meters downstream of the point that it started from. And our final question is, I don't want to be 85 meters downstream. I want my boat to go directly across the river. So, we previously calculated that the boat will actually travel, when I give it a speed of 6 meters a second in a current of 5 meters a second, it's actually going to travel in that direction, which we previously calculated was 40 degrees in a downstream direction. So which way should I point my boat in order for it to go directly across the river? So a lot of people's first reaction there is, well, if it's going 40 degrees in the downstream direction, all I need to do is point it 40 degrees in an upstream direction, and then it will go straight across the river. So let's try that. If I point it upstream 40 degrees further upstream from the way it was pointing, which is about there, where does the boat actually go? Well, we can see it's not going directly across the river. So unfortunately, our solution isn't quite as simple as that. So how do we figure out what the boat is going to do? Remember, what the boat actually does, its net velocity, is the sum of what the motor is doing to it, the speed and direction the motor is moving it, plus the speed and direction that the current is moving it. So the first thing we need to figure out here is, what is it we're trying to work out? We want to know which way to point the boat. So what we're looking for is something about the motor speed. And that's not necessarily immediately obvious, because you might think, well, we know the motor speed. The motor's pushing it at 6 meters a second, which is true. But we don't know which direction the motor is pushing it. So while we know something about the motor velocity, we don't know everything. And it's the other bit that we're trying to find. So now that we know that it's the motor velocity we're trying to solve for, well, if the net is the motor plus the current, then the motor velocity must be the net velocity minus the current. And as you already know, subtracting a vector is the same as adding its opposite. So all we have to do to figure out the motor velocity is add the opposite of the current to the net velocity. Again, that might seem undoable, because we don't know how fast the boat is going to cross the river. It won't be 7.8 meters a second anymore, because we've changed all the directions. But we don't need to know that. We do know something about the net velocity. We don't know how fast the boat is going to cross the river, but we do know that we want it to go straight across the river. So our net velocity is going to point straight across the river, due north in this example. Because I don't know how fast it's going to go, I don't know how long to draw that arrow, which means I can't draw a scale diagram, but I don't need a scale diagram. I know my net velocity is going to point that way. Now I'm going to add the opposite of my current velocity. Well, my current was 5 meters a second going east, so the opposite is 5 meters a second going west. And the sum of those two, which is my motor velocity, is the vector that points from where I started to where I finished. And I need to know the direction, that angle there. Once again, it might seem at first we don't have enough information to solve the problem, but remember, although I don't know which way my motor is pushing the boat, I do know how fast it's pushing the boat, 6 meters a second. So I know the length of that arrow. And now I'm looking for that angle. I've got the side opposite the angle. I've got the hypotenuse. Opposite over hypotenuse is sine, so that angle is just going to be the inverse sine of the current velocity, current speed, 5 meters per second, divided by the motor speed, 6 meters per second. And when I do that calculation, I get an angle of 56 degrees. So that angle is 56 degrees, so the direction, I'm going north, then I'm going 56 degrees to the west of north. So the direction I need to point my boat is 56 degrees west of north. Let's see if we're right. So I'm going to give my boat a speed of 6 meters a second in a current that's flowing to the right at 5 meters a second. I need to angle my boat 56 degrees further upstream, which is about there, not quite. Try and get that right. There we go. Now let's see where the boat goes. And now we can see our boat is traveling straight across the river. If I show the sum there, the net velocity, I'll show the net velocity, there it is, straight across the river. And if I wanted to do so, I now have all the information I need to figure out things like how fast will the boat be crossing the river? What's the length of that red vector? And knowing that, I could then figure out how long the boat would take to cross the river. But we'll leave those kind of questions as exercises for you.